All right, welcome to ECE 4305, Advanced Hardware Description Language using Verilog. In this video, what I want to do is I want to show you what we will cover in this course. So this course, I'd like to think usually about it as 3 parts. So the very first part is going to be hardware description language. I will be using SystemVerilog in this course, not Verilog. All of you are familiar and have used Verilog before in a previous course. It's a prerequisite to enter this course. So you're going to see that the very first part of the course is an extremely accelerated part, and its purpose is to review hardware description languages, introduce SystemVerilog as opposed to Verilog, so it will remind you how Verilog worked and how different is SystemVerilog from it. I'll be creating a separate video just to describe the differences between SystemVerilog and Verilog so that you understand it. But the first few weeks, which is just the first third of the course, it's going to be hardware description language. In the two last thirds of the class, you're going to see that we will be building this particular system that you see in here. And this system consists of 3 parts: a microcontroller unit, memory mapped I/O subsystem, and a video subsystem. Okay, so the boxes you see here are either colored gray or white. The white one we're actually will be writing HDL for. So we're going to be using whatever we cover in the first part of the course, which is SystemVerilog, to design and implement that part of hardware. Anything in gray is typically used, or it's just basically off-the-shelf IP or intellectual properties that Xilinx provides. For example, we will not be designing a processor or some sort of a memory controller. We're just going to take it off the shelf because it's not the purpose of this course, and it's pretty complicated to design these particular parts. Okay, but anything else, we're going to be using SystemVerilog to do it. So the top here, which is the microcontroller, you're going to see that we basically are taking it off the shelf. And usually microcontrollers, as you probably know, are programmed in assembly or C or something like that. We will be using C and a little bit of C++ to actually program this microcontroller. And this program in C and C++ will control the hardware you design in SystemVerilog. So the purpose of this course is to introduce hardware software co-design. You will be designing the hardware and implementing it, and you'll be designing the software to control the hardware and implementing it. Its purpose is not to introduce you or not to be basically a course about SystemVerilog. Verilog is just to show you how a whole digital system actually works from beginning to end and just give you an overview. But in the meantime, since SystemVerilog is a good tool, we're going to be just using it and you will learn it along the way. So the second 2 parts of the course are basically the memory mapped I/O subsystem and the video subsystem. And the memory mapped I/O subsystem is just basically a little system, and we're going to be designing it completely from scratch. And that subsystem has basically I/O, kind of like what you saw in microcontrollers, but you will be designing these I/O. So you'll be designing the UART. You'll be designing the timer, you'll be designing the UART communication protocol. You'll be designing a general purpose output, and you're implementing it on the FPGA and connected to the LEDs. You'll be designing a general purpose input, and you'll connect it to the switches on the Fpga board. You can go all the way to basically 64 of these, from 0 to 63, which is 64 of these input and output systems. But we will not design all these 64. We're going to be doing basically between 10 to 13 depending on the time in the course. Okay, some of these will involve accelerometers, some of them will involve some SPI or I2C communication protocols and so forth. We'll be designing the hardware, writing the SystemVerilog for it, designing a driver to communicate with the microcontroller, and letting the microcontroller program, which is written in C, control all of this and do something useful. Okay, the last part of the course is going to be a video subsystem, and some of you might think, well, a video is an output, so why don't you just put it in the memory mapped I/O, since an O in the I/O actually stands for output? And the answer is the following: all of these outputs can actually operate concurrently in parallel. All of them can be on at the same time. But a video subsystem is a little bit different because it's an example of a streaming processor or a streaming system. What it does, it takes some sort of a pixel, for example, and you're going to see it goes to one box, which is this one here. It gets processed, and then that pixel gets pushed to the next box. It gets processed and gets to the next box and gets to the next box. All the way it goes through all the boxes, gets processed along the way, and then you're going to see it outputted to the VGA monitor using the VGA port that the one we have on the board. So the whole system is basically the whole course is 3 parts, and the system in 3 parts, but you get the idea. So we will have a few labs, about 13 labs, more or less, maybe a little bit less depending on the time. And I want to just show you one of these labs in here, so I'm going to just show you a demo. So let me switch to that demo. All right. So what you see in here is the Fpga board, the one that you're familiar with. But yours might not say Nexus 4 DDR, might be a little bit different. This is just an old name for it. Okay. So what you see here in this system, and this system does not use, for example, the C code. What it does, it uses SystemVerilog, and you're going to see it, but it uses memory and ROM and whatnot. We'll get to the implementation in here. But you're going to see in this system that we have switches in here, and these switches, whatever I control them, numbers get changed. But effectively, I'm actually controlling the number that is displayed on this part, which is the right part, okay? And the system is just converting temperatures. This is 43 Celsius to 109 Fahrenheit. For example, let me just repeat, you're going to see that whenever I was at 0, which is the freezing point for water, it's 32 Fahrenheit, which we know already. And you get the idea, so you can actually do all of this. What's more interesting about the system is actually you can go to the last switch on the left side, actually switch it, and what you see is you flip now 53 Fahrenheit is now 12 Celsius and so forth. So I flipped basically the input. The input now I still can change it, but the input is in Fahrenheit, it becomes in Celsius. You'll be designing and implementing systems like this. One of the more interesting ones, which I couldn't find the code for it, so I'll have to code it later in a few weeks. It's basically an accelerometer in here. There's an accelerometer on this board, and that accelerometer can actually detect all these movements I'm doing. And what we're going to be doing is we're going to tap the table, and we're going to see that that accelerometer will actually detect this tapping, and it will turn on LEDs accordingly. And it's a really interesting lab. I hope that you do enjoy this lab. I definitely enjoyed preparing it and teaching it. So hopefully you enjoy the semester.